I'm a PhD student, like Francois said. My supervisor is Yuval Tal, and we're from the Ben-Gurion University in Israel. And this is the, right?
Yeah, you might have to make the slides because the recording started.
If this doesn't work, yeah,
click on the slide once, then it's sort of back in focus, and then you can switch with other means.
okay.
And then maybe the next one.
Okay, thanks. So this is a seminar outline. I will talk a bit about in background about earthquake ruptures and fault geometry and the effects of fault bands on earthquake ruptures. Then I'll show our experimental setup and how we analyze our data, and show some results about first ruptures on planar interfaces and then ruptures on interacting with fault bands and the effect of fault bands on the near field seismic signal, and a bit about other lab projects that we work on. So first about earthquake ruptures, we can see here a simulation of an earthquake nucleated and propagating along a fault. And you can see that the rupture has a few characteristics. So I'll start in the initial part. You can see here the rupture. Here it nucleated and expanded, and this whole area is a rupture. So the rupture is quite large and encompasses this whole area, meaning it's a crack-like rupture. So in front of the rupture, the fault is locked. But after the rupture, there is a long slipping region, and slip accumulates along this entire region. So we got slip velocity before the rupture is 0, and after it, it's not above 0. So this is a crack-like rupture. But as the rupture goes, it changes to this shape. You can see it here. So this is the rupture now. It's very thin, and it's a pulse-like rupture, meaning that before the rupture, the fault is locked like before, but after the rupture, the fault is also locked, and the rupture front is the only place that slips or the slip accumulates. So after the rupture fault, slip doesn't accumulate, and the slip velocity is 0. So we see two styles of rupture for the same rupture, so the rupture change. And now you can see it propagates. And now I'll talk a bit about fault geometry and how it affects the rupture, at least what we know of. So we know that ruptures affect fault geometry. Fault geometry affects the ruptures. And you can see here for the 1999 Izmit earthquake, and you can see here the surface rupture of the earthquake, and it stopped. It's nucleated here and propagated to two sides or bilaterally, and stopped on two stepovers here and here. And we don't know for sure, but we can correlate this rupture extent to some geometric features, in this case, stepovers. And here we can see a surface, a fault trace in Tibet that shows repetitive rupture termination, so not a single rupture, but various numerous ruptures for hundreds of years that don't pass to bands of 20 degrees deviation from the general strike. So we can see here some connection between the fault geometry and the rupture extent. This can be seen also in numerical modeling that shows for a releasing band, meaning a band that extends dynamically during the rupture propagation, above around 34, 35 degrees, rupture couldn't pass the band. Okay, so and for a restraining band, a band that compresses, rupture couldn't pass a band of about 18 degrees. So the band angle or the deviation angle from the strike affects the rupture passing, and we can see here for both empirical results from real surface ruptures and simulations, passing probability of a rupture versus band angle. So the higher the angle, the lower the passing probability of a rupture. But we are interested not only in the passing probability, but how it affects rupture dynamics, even if the rupture passes the band. And we can see some examples of how it works from two real earthquakes. So this is the 7.7 Komodorski Island earthquake, and we see that the rupture started here and went on this branch, then leaped across a step over, a releasing step over, and accelerated. So here it was about the rupture propagation velocity was about 2 to 3 to 2.7 kilometers per second, but then it propagated to 5 kilometers per second, which is supershear velocities, which I'll talk in a minute. And here we can see, so this is after a releasing bend here, or a releasing step over, and here we can see the 2018 Palu earthquake, and we can see here the fault, and the upper part moved left or north, and this moved south. And the rupture started here, but very soon after its initiation, around this area where there is a small restraining band, the rupture also accelerated to supershear velocities. So we see maybe some connection between the geometry and how it affects the rupture when the rupture passes the bend. And a bit about fault rupture velocities. So I'll talk about sub-Rayleigh velocities, which is slightly less than the Rayleigh wave speed, and supershear velocities, which is above the shear wave speed of the rupture propagation velocity. And both are very distinct and different displacement fields around them. So if we'll regard the rupture as a moving point source, radiating waves that it moves, we can see that here in time equals E0, the rupture is here, and time equal delta t, the rupture moved, but here it moved less because it's slower than here, and it both released a wave, shear wave, and we can do in time delta t, the rupture moved more and more and more, and we see they are very different, in very simple way, you can see very different deformation patterns around the rupture, and this as the rupture is confined in the shear waves, but here the rupture is passing the radiating shear waves and creates this triangular shape, which is called a Mach cone. It's a conic shape actually in 3D. And this Mach cone is it's a supershear. It infers the supershear velocities, and it also appears when planes move to supersonic. And these are some of the inferred supershear earthquakes, and some of them are very devastating. So supershear earthquake, and specifically the Mach cone, is related to very, very destructive and intense ground motions. And finally, for the background, we see here simulation by Abdel Magid of the 2023 Kahramanmaraş earthquake in Turkey. So a very devastating event, and we can see that the rupture has many episodes. It went to supershear, it went back to sub-Rayleigh, it changes direction. We can see it coming from here and then left and then right. So the rupture is very complex, not like very simple rupture that we saw in the simulation earlier. And Gori evidence show that many large earthquakes do have very complex ruptures, and which include various episodes and changing of the rupture style. And our research goal is to study experimentally how fault bands affect the rupture dynamics, velocity, and style, and can it explain at least some of the rupture complexity. Okay, so this is our experimental setup. We pre-cut two PMMA plates, one rectangular PMMA plate to two plates along geometry that we define. It can be planar, it can be with a bend. And so we control the geometry, and we stress the two plates together. And then we nucleate a rupture here, which then propagates and is captured by this ultra-high-speed camera, capable of filming at up to 5 million frames per second. And so it captures this field of view. And it can catch the rupture propagation, actually. And the reason we use PMMA is that we know that nucleation size and many other important factors of the rupture dynamics are proportional to the shear modulus. So the lower shear modulus of the PMMA allows us to downscale the entire system from tectonic size to a laboratory specimen. And our laboratory is a similar setup to the dynamic fracture laboratory in Caltech of Aris Rozakis and Vitor Rubino. And this is part of the publication. So it's a very, very fruitful laboratory and very useful setup. So this is their laboratory, and this is our laboratory. They actually helped us with establishing it. And we can see here the specimen and the press that uniaxially loaded here. And this is the camera. These are two flash heads that illuminate the sample very brightly during the rupture propagation. This is the pulsar that nucleates the rupture. And this is a timer that times everything together so that we can capture the rupture propagation where we want it here in this section. And now we see how an experiment looks like. So this is the sample and this is the press. Okay, so obviously it's a very quick experiment, and we can do multiple experiments per day. And we can see here that upper plate moved left and the bottom plate moved right, and we are interested in this area along surrounding the interface. So this is what the camera sees. It's a part of the specimen, and you can see the interface here. In this case, it's a planar interface. And if we enlarge this area, we can see this area. Now we'll see how it looks during an experiment. So look around the interface, and you'll see really the plates moving. Now. Okay, so we really can see the plates moving, but we are interested not in how the plates moving, but really quantifying it to the pixel resolution. And to do it, we use a method called digital image correlation, or DIC, which is becoming increasingly popular. And you can see here some of the researchers that use it in earthquake laboratories, at least some that I know, maybe there are more. What DIC does, it draws a rectangular area. We can control the side of the rectangle. In this case, it's 61 squared pixel. And it tracks this rectangle movement along the frames. So this is the first frame. And now we see how this rectangle moves, and this rectangle moves during the experiment. So this is the reference. This was the thin line was the first frame here, and the thick lines in the end of the experiment. We see that we have left moving rectangle here, and here it moved right. And the DIC assigns this displacement of the entire rectangle to the central pixel. And when we do it to the entire field of view, we can get, with a bit of a filtering Gaussian and noise and systematic noise of the camera, we can get these displacement maps. We give us the displacement of each pixel in each frame. Okay, so we can see here two image frames, and these are the displacement that we analyze using the DIC from these exact frames, left and right displacements and up and down. And you can see how the rupture propagated from left to right. So we can take these displacement maps and derive them spatially to get the strains. And from the strains, we can also get the stresses using the elastic modulus of the material. And we can get really like a 2D image of the shear stress in this case, or the change in shear stress along the experiment. So in this exact frame, so we see an increase of shear stress and decrease, which is suits to what we know about the rupture. And we can also derive them by time to get the velocities. So we can see here maps of the snapshot of the velocity, horizontal and vertical, and we can combine them to see the absolute particle velocity. So the absolute velocity of each pixel in each frame. And this is main data that I'll show here. And we can also get other stresses, not just shear, but normal and horizontal and fault parallel stress, and strains, accelerations, rotations, diversions, etc. So a lot of things we can get from just simply imaging the rupture propagation. And now we see how an experiment looks in the evolution of the absolute particle velocity, or the velocity magnitude. So this is what you see, this area, which we picture, the rupture nucleated here and will propagate. And in this case, the interface is inclined in 28 degrees with regards to the horizon. This angle defines the shear to normal stress ratio. Okay, so 28 degrees, it gives us some shear to normal stress, and we nucleate the rupture, and now you see what we see. So you can see the rupture coming from left to right. You maybe see some, it's not that smooth because still it's a camera and it's real data, so we have some noise, but I think you'll agree that it's very clear that we have this shape of the rupture front, which is a distinct shape of a sub-Rayleigh pulse. And if you don't believe me, here are numerical simulations by Melo et al. Of a sub-Rayleigh pulse, and you can see they're very, very similar. So we can regard it as like a high confidence. And here below we can see the slip velocity evolution along the interface with time. So the slip evolves from with time, and now we'll let it evolve. And slip is the fault parallel velocity above the interface minus below the interface. We can see how it evolves. And the slope of this thing is actually the propagation velocity. And in this case, it's slightly less than the Rayleigh wave speed. So it's a sub-Rayleigh rupture. And we can see that below it, there is no slip velocity, so no slip accumulation, and it's a pulse. So it's a sub-Rayleigh pulse. And this will be a reference for the band experiments because we believe that large earthquakes mostly propagate as sub-Rayleigh pulses. But mostly, like we said, it's a complex rupture, but this is a reference. But before I talk about bands, I'll show another experiment of a planar interface with higher alpha, so higher shear to normal stress ratio. In this case, also the field of view is smaller that we image, so the camera is closer to the specimen. And now we'll see how it looks. The rupture is very different, and we can see here it has this conic shape, which is actually the Mach cone, and it's preceded by a pressure shock here. And this part is called a trailing Rayleigh, a part of the rupture that travels in Rayleigh wave speed, and we can see it's like we saw in the supershear example, so it's a supershear rupture. And if you don't believe me again, here are from the same paper, numerical simulation of supershear rupture, and we can see that the shape is very similar, so again, high confidence. And let it roll, and we can see here the propagation velocity, which is 1.5, more than 1.5 times the shear wave speed, and we can see also here, this part is the trailing Rayleigh. Okay, but we're here to talk about bands, and I'll show some experiment with bands. So this angle is 28 degrees, so like before, a reference is a sub-Rayleigh pulse, but now it will interact with a 12.5 releasing band. Okay, so the rupture arrives like before the sub-Rayleigh pulse. Now it interacts with a band. And it transforms to a supershear crack rupture, like the same shape that we saw before. And I remind you, this is real experiment, so it's not a, it's like it's just a very, very simple analysis of the imaged frames. And we can see here in the slip evolution how the slope changed from this to this, so transform from sub-Rayleigh to supershear, and we can see here the trailing Rayleigh behind it. And now we see for a 20 degrees restraining band, so a band that compresses during the rupture propagation. And this is actually considered high angle, like we said before. In the numerical simulation that I saw in the beginning, that 20 degrees couldn't pass rupture, though this is what we'll see here. You see the rupture coming from the left and interacts with the band. Now we can see here in the slip evolution that the rupture stopped, so no slip. The slip only arrived, see here, just under the band, but it didn't pass the band. But we do have some deformation left. This deformation is the fault normal component. It's exactly on the border between. You can see here another arrow. It's the fault, only the fault normal component passes the band. So the band acts as a kind of polarizer. The rupture came pairing both fault parallel and fault normal components, but the band stopped the fault parallel component and let the fault normal component pass as a sort of a shear wave speed. You can see it propagating, but slip doesn't continue. So again, the fault parallel component stopped, but the fault normal component passed the band. So it's not simply the rupture did arrest, but some component of the rupture did pass the band. Now we see a lower angle restraining band, so lower deviation angle from the strike. The rupture arriving like before as a sub-Rayleigh pulse. Now it interacts with the band. And we see it's distorted. It's not as distinct and clear like before. And it's actually not completely polarized, but out of phase. So this is in front of it, it's the fault normal component, and here behind it's the fault parallel component. So the band slowed down the fault parallel component, but didn't stop it completely. But the fault normal component passed, so it's out of phase, not in phase like it was before the band. But now notice what happened on the band when the rupture continues to propagate. We have this secondary backward propagating ruptures, which actually propagates as a supershear rupture. Okay, and now you see another one coming with this triangular shape. So we can see here how the band caused the decrease in the slip velocity, but after the rupture passed it, we got these backward propagating supershear ruptures that nucleated around the area of the band. And actually these backward propagating supershear ruptures is phenomena that is recently been shown in real earthquakes. And we can see here it's occurs naturally on these bands. We didn't expect it, and it still occurred. And for last of the examples, I show 17.5 restraining band, so a high angle restraining band, and it will stop the rupture, but something interesting will happen after it. So the rupture comes and it sort of breaks on the band. Slip rate stops. Now there's a very, very small rupture coming from the left, another one. This rupture is probably an effect of the left edge. So the rupture initially nucleated here and propagated bilaterally. So we see the right propagating part of it, but the left part probably hit the band, the edge, and came back, and this is what we see here. And this is a part of the rupture that we can, it's hard for us to control. It's not like the first part that we see, but it's the second part of it. So we are not focused on it in our main experiment, but still I want to show it because it's a very interesting result. So we see the rupture coming from the left, and notice what happens when it reaches the band. It unlocks it very, very, very intensely. And you can see it again, and there is a bilateral supershear rupture on the band. So we can see here how the rupture arrested, the first rupture arrested, and then a second rupture came and caused a very intense unlocking of the band. So it's like a dynamic effect of something that we suspect to see more static or seismic cycles. But still, I think very interesting. And now we'll look at some summary of most of our experiments. So this is our reference, like I said, a planar interface, and we can see that it's a sub-Rayleigh pulse. And this is for a 10 degrees restraining band. So on the band, you see this is the geometry. So on the band there is a decrease in the slip velocity. But after it, the rupture continued to propagate smoothly, and there is no significant change from the reference. But in 12.5, it's the experiment we saw before, there is this slip decrease, and after the rupture passed the band, there is backward propagating supershear ruptures. For a 10 degrees releasing band, we see this transition from pulse to crack. So it was pulse and planar, and in releasing, we see this slip velocity behind the rupture. So it's a crack-like rupture. And here we can see this transition, there was changing slope from sub-Rayleigh pulse to supershear crack for 12.5 releasing band is the experiment that we saw. For a 15 degrees restraining band, it actually We now know that it's like a boundary angle, so some experiments don't pass the band, but this is an experiment that did pass the band, and I wanted to show it. The rupture actually stops or rests for 20 microseconds, but then it comes back with these backward propagating supershear ruptures like we saw before. And for 20 degrees, the rupture arrests totally, but like we saw, the fault normal component do pass the rupture. And for 15 and 20% releasing bands, we can see this at 15 and 20 degrees, we see this transition from sub-Rayleigh pulse to supershear crack like we saw before. And now I'll show a bit the effects of bands on near-field ground motion. So we can take each pixel to be like a seismic station and let it record the velocities during the experiment. This is what we see here, the fault parallel and fault normal velocity, both close to the fault and further away from the fault. And before the band and after the band, and this is a reference, a planar interface. So this is the seismic signal of a sub-Rayleigh pulse. And this is a 12.5 releasing band. So we see that after the rupture, we see this significant amplification from the planar. So this is actually the supershear transition. So the supershear front, which is more intense here, but in general, it's all very intense. And even before the band, we see this simplification, which is the transition from pulse with no slip to crack where there is slip behind the rupture. So this is the band cause fault parallel amplifications both before and after the band. For a 12.5 restraining band, we see that the signal is largely the same to planar, but before the band, we see these two peaks, 1 and 2, which are the backward propagated supershear ruptures that cause very intense but short amplifications before the band. And for a 20 degrees restraining band, we see the polarization effect. So before the band, the rupture is very similar to the planar interface, but after it, there is no slip velocity, so or no fault parallel velocity, so it was arrested. But in the fault normal velocity, we can see the rupture pass very smoothly, but it did decrease by about 50%, but it didn't stop. So it's the polarization effect that I talked about before. And if we look at everything together, we see that the fault parallel velocity is very, very different in all the experiment, but the fault normal is not that affected, like we see here. So the band mostly affects the fault parallel component, not the fault normal. And to summarize it, we showed here a first and direct full field observation. So full field is like 2D surrounding a band of dynamic ruptures interacting with releasing and restraining bands of different angles. And depending on the band angle, these effects range from slowing and arresting the ruptures to accelerating up to supershear velocities. So, and now I'll show it. So for 10 degrees restraining band, the rupture is largely unaffected, but between 10 and 15 degrees, we see these backward propagating supershear ruptures that are triggered after the rupture passed the band, and they cause fault parallel amplification before the band. And for 15 to higher angles, the rupture arrests, see here, but the fault normal component passes. So we see this polarization. For a 10 degrees releasing band, we see pulse to crack transition, but for higher degrees, we see the transition from sub-Rayleigh pulse to supershear crack, like you see here, and causes fault parallel amplifications both before and after the band. And we see up to a 15% decrease in the fault normal velocity, but not something very significant compared to the fault parallel velocity. And now I'll very briefly talk about other projects that we work on in the lab. So we test here we see an outcrop of a fault in northern Israel, and we see that it's very, very, the geometry is very complex. It's not just a single band, but both in fault strike parallel and deep component. And this is actually fault geometry is often more complex than just one band. And we are interested in how this complexity affects the rupture. So we see here an interface of a specimen. We can see it here. It's of course the geometry is, maybe you don't see it, but it is rough. And we are interested in how this roughness affects the band, the ruptures, sorry. Another project that another PhD student called Gosh works on It's the effect of off-fault damage, so small cracks that are quite close to the fault but not on the fault. That and they check how they affect the rupture dynamics, and actually they have very interesting result, but you need him to explain it to you. And finally, one thing that we recently started setting up is a biaxial loading. So not only the axial, but another loading from the side, which will allow us to do seismic cycles. So not just a single rupture, but many ruptures. And we have another high-speed camera, not as fast as the camera that I showed here. But this will allow us maybe to see two timescales, the entire cycle timescale and the single rupture timescale. And we have some new laser velocimeters, but this system is not still operating, but we are working on it. And that's it. That's my talk. Thank you very much.
So it's very